Good afternoon.
Hey. Thanks for finding that typo. It was very small.
Yeah.
No, I mean the index was an I and a 1. It's very hard to distinguish them from a distance.
Yeah.
Anyway, thanks.
So you're welcome.
And thanks for reading the paper.
Yeah. Yeah. I enjoyed it. At least however much I read. I tried to read the two sections 4 and 5.
Right. I mean,
and I feel like I got some of it, but I don't still have all of the intuition. So. Yeah.
So today I'm going to try to give mostly the intuition about the main theorem, the existence of these groups, and then I'm going to give the not much intuition, but just a few words about the other parts. But in fact, if the intuitions for each of these theorems are very, very simple. It's just that there's a lot of technical things that must be done, like ensuring that things match up and that you can communicate cosets or things like that through local rules. That's always messy to test, but it's not hard.
Yeah.
That takes up space.
Yeah, that's a nice use of paradoxical decompositions.
Thanks. Well, I guess it's not the first time that it's been used. Like these, I haven't read the original paper, but I guess that the construction of translation-like actions by White show that the geometrical von Neumann analog of the geometrical analog of von Neumann's conjecture is true. Also uses something like that, right?
Yeah, I think so. Right. I think you're right. I mean, yeah, it is something similar. Yeah.
So it seems the natural way to embed trees in non-amenable groups, right?
Yeah. Yeah.
Yeah. So in fact, the first time we proved this theorem, we wrote it in terms of translation-like actions. We just used this theorem that says that there are translation-like actions of the free group of 2 elements on every non-amenable group, finitely generated. And then we realized, it's actually nicer if you do it just with paradoxical decompositions. It's direct. So we took out those things.
Oh, I see. Oh, okay. That's nice.
Yeah. Wow. So first we proved the theorem for F2 times F2, and we wanted to use that theorem, but we realized that it was essentially the same as proving it for any product of non-amenable groups through paradoxical decompositions.
You know, there's a paper of so it's reminded me of it's a paper of Nekrasovich and Gabor-Peta on scale invariant groups. So these are groups which have a, so the group has a finite index subgroup, which is isomorphic to itself. And then you can continue on down. So you have a chain of finite index subgroups, each isomorphic to the original group, and the intersection is trivial. But you can get groups like this that are non-amenable. I mean, like Z squared obviously has this property, and it's used in Berger's proof. I mean,
I thought those were called non-co-Hopfian or something like that.
Yeah, right. Right. I forgot. Right.
But I don't think I've read that paper.
Yeah, here it is.
Huh, okay. Okay, I'll take a look at those. Maybe, who knows, maybe they
I
turn
mean,
out to be.
it just seemed, it sounded like kind of like, okay, you have this kind of self-similarity. I don't know. It doesn't
Right.
seem directly related, but
What I'm more aware of is the self-similar groups of Nekrashevich through transductors. So when he defines these finite transducers that define actions, and if it turns out that there's some post-critically finite set, then every Schreier graph has some sort of scale invariance, so it looks like a fractal.
I see.
I know a little bit more about those, but I'm not really, I don't really know that paper that you showed me, but I'll take a look at it. It looks interesting.
Okay, so I guess it's 2:05, so we should, I guess it's time to get started. So we're happy to have Sebastian Barbieri from University of Santiago of Chile talk about self-simulable groups. So go ahead.
Thank you very much, Lewis. So, all right, thank you very much. So the goal today is to talk about a class of groups which have a very, very strong universal property in terms of their dynamics. That property I'm going to explain in detail later on, but essentially it means that any action over a zero-dimensional set that I can properly describe through a Turing machine is the topological factor of something very simple, which is a subshift of finite type. This is work that I did with Mathieu, Sablik, and Ville Salo. So I mentioned them before starting. All right, let's get right into it. So let me try to motivate my theorem through a theorem on group theory that I love a lot. So most people are probably acquainted with finitely presented groups. So whenever I have a group, I can give a presentation of a group. Finitely presented groups are those that I can give through finitely many generators and finitely many relations, saying that a particular word in the generators is the identity, right? So set square is finitely presented. A lot of groups that one is familiar with are finitely presented. And there's another definition which is way, way larger, which are finitely generated or recursively presented groups. Those are groups that are given by finitely many generators, but the relations, maybe it's not possible to give finitely many of them that describe the group, but you can somehow give an infinite number of them and enumerate them in some recursive way through a Turing machine, right? So that's a very large class of groups. Very interesting groups are recursively presented, but not finitely presented. For instance, Grigorchuk's group, the famous Grigorchuk group is one of those. So it's kind of interesting to understand those. And there's a huge theorem of Hickman on 1961 that says that every recursively presented group, I put finitely generated in parentheses because it's not really necessary. I just don't want to define the general ones. It occurs as a subgroup of a finitely presented group.
Is the converse true? Is the converse?
Sorry?
Is the converse true?
That every what would be the converse? Sorry?
Every subgroup of a finitely presented group.
Yeah. Every subgroup of a finitely presented group is recursively presented. Yes. So it is an if and only if. And in fact, you can find a single finitely presented group that contains all recursively presented groups. So it is very, very strong. There is a universal finitely presented group. Okay, so this is a huge theorem. It allows you to, for instance, trivially prove that there are finitely presented groups with undecidable word problem. That was a huge theorem before. After this theorem was proven, that's a corollary. So it's very nice and it allows you to prove many interesting things. So what I'm searching for is the same kind of theorem, but for dynamical systems, for actions of groups. So just to remind a little bit, I'm going to be interested in topological dynamics for this talk. I'm going to consider actions of a countable group through homomorphisms on a compact metrizable space. And moreover, I'm going to restrict things a little bit more. I want to be able to describe the action and the space through a Turing machine. Okay, I'll remind you what that is. Okay, so I want to generalize this Hickman theorem. So one should ask, what would a dynamical analog Higgs theorem would look like, right? So I'm not going to try to justify this too much. I'm going to think of subshifts of finite type as finitely presented groups. I'm going to explain what they are in a moment. And I'm going to try to replace recursively presented groups by effectively closed actions. And I'm going to try to search for a statement of the form, well, every action which can be described by a Turing machine can somehow be obtained in some nice way from a subshift of finite type. Okay, I'm gonna precise all of these informal terms, such like nice way or obtained, in a moment. Okay, now, why subshifts of finite type? Well, essentially because I could look for another decent finitely presented class, but this looks like the most natural one, and it already satisfies a lot of nice properties, so it's something one thinks of as a basic rig on dynamical systems. Okay. Okay, so just to remind you, this is virtually the same slide that I used last week. So subshifts of finite type noun groups are just, well, I consider the set of all mappings from a group to a finite alphabet with the prodiscrete topology, and I take the shift action that just moves things around. I'm going to call a subset of a to the gamma a gamma subshift if it is closed in the prodiscrete topology and the invariant under translations. And I'm going to say that the subshift is of finite type if I can describe it through finitely many forbidden patterns. So there is a finite set of the group and a finite set of functions from the group to the alphabet, such that a configuration Y is in the subshift of finite type, if and only if I don't see any of those patterns appearing anywhere. Okay. So same example as last week, sorry to bore you. The hard square shift, I can take maps from set square to 0, 1, and I just forbid two patterns. Well, the set of all configurations respecting that constraint is a subshift of finite type. I could do the same thing on a free group, right? I could forbid, I don't want to see any 2 1s after going through a generator. Well, that gives me a subshift of finite type on the free. Okay, so again, I'm just reminding the definitions from last week. What does it mean that a set can be described by a Turing machine? Well, I just, for any word on the alphabet 0, 1, I can consider the cylinder set of all configurations in the Cantor set that begin with the word. That's the cylinder generated by the word. And I'm going to say that the set is effectively closed if there's a Turing machine that enumerates a sequence of words that describe its complement. Okay, so essentially, I can tell you if I wait long enough and I run my Turing machine for a long time, I can tell you whether if a configuration is not in the set, because I'm eventually going to detect that the prefix of the word of this configuration was in the complement, right? Okay, and I also have to describe what it means for an action to be described by a Turing machine. So if I have a group which is generated by a symmetric set, I can consider the set of all configurations on 0, 1 to the S to the N. So that means all infinite sequences on 0, 1 to the generators, such that if I project to a particular S, I obtain an element of X. And furthermore, these things respect the action. So it's better explained through this example downstairs. Imagine my group was Z. So I just have Z acting on a space. And in fact, my space here is going to be the whole Cantor set, 0, 1 to the N. And I'm going to consider a very simple action, which is the odometer, the binary odometer. The binary odometer does the following. I look at configurations of zeros and ones. And when it finds the first 0 to the left, it turns it into a 1. And it turns the ones before it to 0. Right? So it just adds 1. Right? So what is this set Y that I described above? Well, imagine here I have a configuration X in 0, 1 to the N. That's in the middle. And I want to code the maps by +1 and -1. So in +1, I will just code the action. So if I apply the odometer to this configuration below, I would get 0, 0, 0, 1. And in -1, well, I want the inverse action. So the predecessor of that would be 0, 1, 1. And what I'm going to do is I'm going to get this new thing and I'm going to code it as an effective set. So this set of 3 symbols is y0, this second one is y1, so forth. So that gives me a point, y in y. And my definition of effective action is that for some set of generation, symmetric set of generators that contains the identity, this set y is effectively closed. So I can describe its complement through a Turing machine. And that's just for definition's sake, to give a concrete definition, but the intuition you should always bear in mind is there is an algorithm that if I put to run for a very, very long time, it eventually can figure out that a point x is not in the space, and it can also check whether 2 points x and y, one is not the image of the other through some generator s. Okay, so somehow this Turing machine understands the action and understands the set at the same time. Okay, so just for simplicity, and this is not something very restrictive, I will say when it is, we will always suppose that our groups in this talk have the citable word problem. So they will always be finitely generated and have the citable word problem. What does that mean? Formally, it means that there's an algorithm telling me when a word on the generators is the identity, but intuitively it means that I have an algorithm that can construct arbitrarily big balls of the Cayley graph of the group. So somehow I can understand the geometry of the group through an algorithm as well. Okay, that's not restrictive. Actually, the main theorem is still true without this assumption, but I won't say that it's vacuously true, but it's less interesting because if the group does not have the citable word problem, then many interesting things stop being effective. So I'll just take this as an assumption just to not complicate things any further. Okay. Okay, so let me give you an example that I gave you last week because it's going to be very interesting in the last part of this talk. Suppose I have the counter set 0, 1 to the n, and I take 2 sequences of words in 0, 1, u1 up to un, v1 up to vn, which partition the counter set. So the counter set is the union, this joint union of the cylinders defined by the words u1 up to un, and the same, it's a disjoint union of the cylinders given by v1 up to the n. And I define phi to be the homomorphism of 0, 1 to the n that maps every cylinder ui to vi by replacing prefixes of infinite words. Right, so here's the same example that I showed you last week. If I have 0, 0, 0, 1, and 1, those partition the counter set. 0, 1, 0, 1, 1 partitions the counter set. And then this map phi is an automorphism of the counter set. Right? Okay, and there are 3 interesting groups. F is the group of all such homomorphisms where these words are given in lexicographical order. T is the same, but I allow to permute the sequence u1 up to un cyclically once. And V, I don't put any restriction on how I give the words. And these are very famous groups, which are called the Thompson's groups. They are finitely presented, have the citable word problem, so they fit into everything we want. And their natural action is effectively closed. It's just an example of what was before. And now I want to say something else. These groups T and B are non-amenable. And it is a famous open problem whether the Thompson's group F is amenable. Okay, so this is still unknown, and many people have tried tackling this question, and we still don't know the answer.
Why was Thompson interested in these groups? What did he construct?
He was trying to construct simple groups.
Oh.
Yeah, they were trying to construct finitely presented simple groups. So I have to add finitely presented because if not, it's not so hard. And at the time, there weren't so many examples, and these groups are, I think some of them are simple, others are very close to being simple. Okay, I don't remember the details right now exactly.
Okay, thanks.
But it was because of simplicity, if I'm not wrong. All right, so, okay, these are examples. And now I want to repeat the one theorem that I told you last week. This is some sort of related result, which is very interesting. A theorem of Hoffman shows that if I have an effectively closed action of Z, then I can recover this action as the topological factor of a subaction of a C3 subshift of finite type. So for any effectively closed action, you grab the Turing machine, and I can construct a subshift of finite type in Z3, such that if I take the Z subaction, I get some system, which is mysterious, and I take a factor, and then I get my original effective action. Okay, so if you don't know, topological factor just means the image under a continuous gamma equivariant map. A gamma equivariant means that it respects the action, continuity, well. And this factor is kind of nice. So you can, the interesting thing about this theorem is that by using it, you can give me a very complicated effective system and recover some of these properties in the three-dimensional subshift of finite type. So this theorem serves as a black box. You can prove that there are subshifts of finite type with very, very weird properties just by constructing first an effectively closed action and pushing it up through this theorem. Okay. All right. So what I'm going to talk, which is different from last talk, is that along with Mathieu Sablik, we have already given some generalizations of this of Hoffman's result to actions of groups. So we proved some time ago that Hoffman's theorem can be generalized to the following setting. Instead of having an action of Z, I take an effective action of any finitely generated group gamma, and I push it up to a subshift of finite type in any semi-direct product of CD with gamma, if D is larger or equal than 2. So Hoffman's theorem corresponds to the case where gamma is Z, D is equal to 2, and the semi-direct product is just the direct product. Okay, so this is interesting because then again, properties of effective actions can be pushed to SFTs in this setting. And if you don't want to have a semi-direct product, to have a component Z square, you can prove that the same is true if you replace gamma by gamma times H times B with two infinite and finitely generated groups H and B. They could be torsion groups, you don't care. Okay, so there are these simulation theorems that allow you to do this kind of thing outside of Z. And if you try to improve them, it gets very, very hard. But anyway, what one would really like in life is the following. Can we actually have any group gamma such that this diagram is as simple as possible? So let me call this the Holy Grail. We would actually want not to have to take any different group. We don't want to have a subaction. Are there any groups where I can just construct an SFT that factors onto your effective action? So for every effective action, give me an SFT which factors onto it. Can I have something like that? So that's the question we were asking. And now let me say something about, yeah.
Can I just ask about the previous slide?
Yeah, sure.
So just to be clear, so you start with gamma acting on Z, then
on X.
You start with gamma acting on X, then
yeah.
you find a D and a phi such that all of this exists, or you prescribe D and phi in advance?
Sorry, I should have explained better. I start with an effective action gamma on some subset of the Cantor set. And for any D larger than 2 and any homomorphism gamma to the automorphism group of set to the D, so for any semi-direct product, I can find an SFT. So it is for any choice of D and for any choice of phi.
Okay. Wow. Cool.
Yeah.
And
so it is really, you can choose that as you want. It's really the SFT that changes from the effective action.
The only catch is that D has to be bigger than or equal to 2.
Yeah.
Okay.
With D equals to, if I have D equals to 1, then it doesn't work. I can find a counterexample.
Got it. Okay, thanks.
So let me get back to this. So really now I want to get rid of the subaction. I do not want to have this subaction. And I'm wondering, are there any groups that satisfy this? I know that Z does not satisfy that. I can easily find counterexamples. So, well, at first I should tell you something about myself. I am a very negative person. So whenever somebody asks me a question such as this, I tend to say, no, of course it's false. And I try to find a counterexample. partly because of that, I got interested in group theory lately, because most conjectures are false, so I have higher chance of succeeding. Anyways, so I thought about this problem a lot, and after a few years, we ended up proving that in fact these groups do exist. So I should not be so negative in life, and that was what I learned. These groups do exist, and my goal in this talk is to actually convince you that these groups do exist, and actually that the proof is not so hard. So I call this a crazy question because I will try to convince you first that it's very hard for these groups to exist, and then I will actually convince you that these groups do exist, and there are a lot of them, and many groups that you faced in your life are actually self-simulable.
So basically you're saying for these crazy groups,
yeah,
every effective action is sulfic.
Yeah.
In the sense that it's a factor.
In the sense of suffix subshift. Yeah. Yeah. So it's funny because I will show that Thompson's V is self-simulable. And so the natural action of Thompson's V over 0,1 is sophic. So you could say that Thompson's V is sophic. But you shouldn't say that because people would understand that you're talking about and that's an open question. We didn't solve that. I still do not know whether Thompson's V is
But you
sophic.
could cause tongues to wag if you published a paper like that.
Yeah, but that would be, how would you call it?
False advertising. Yeah.
False advertising. Yeah. All right. Sorry. Yeah. So, right. So that means that every effective action is sophic in the sense it's a topological factor of an SFT. All right. So let me give a definition. I'm going to say that a finitely generated group is self-simulable if every effectively closed action is the topological factor of a gamma SFT. And I want to say this, I feel the name is also false advertising. Self-simulable seems too grand. I should say something like groups with self-simulable zero-dimensional dynamics, but it's not that catchy. So I'm just going to call them self-simulable for this topic. Okay. All right. So obstructions. Why did we believe these groups do not exist? Well, amenable groups can never be self-simulable. I'm going to show that in a moment. So look at non-amenable groups. Well, groups with infinitely many ends, such as the free group, cannot be self-simulable. All right, you'll say, well, let's search in one-ended non-amenable groups, but some one-ended non-amenable groups are also not self-simulable. So we showed, for instance, that any multi-ended group times amenable is not self-simulable. So you start getting very disappointed and you think these groups do not exist. And then we showed, oh, that's not yet the point. Before telling you which groups are self-simulable, let me argue that amenable groups cannot be self-simulable because amenability is going to be useful. So probably most of you already know what amenable means, but let me be pedantic and repeat it. Let gamma be a group. Let me take a finite subset and a constant delta. I'm going to say that the subset of the group is k delta invariant if kf symmetric difference with f is smaller or equal than delta times f. So this is the picture. You grab a finite set k, and you essentially want to find a set f such that if I move it by k and I take the symmetric difference, this border is very small with respect to the original set f. So for set square, it's easy to see that if you take any k and any delta, and you take f to be a big enough box, eventually that's going to happen, right? So I'm going to call the groups where such sets exist amenable. A group gamma is amenable if for every k delta, you can find a set which is k delta invariant, right? So essentially you can find large sets that are as invariant as you want. Okay, I bored everybody with this, but this is the point I want to make. Amenable groups cannot be self-simulable because of entropy. So some people know that if you have an amenable group, there is a way to associate to every action on a compact metrizable space by homomorphisms a non-negative real number called its topological entropy, which is a non-negative real number between 0 and plus infinity. Okay, that's something interesting, but it satisfies some nice properties. If your action is expansive, topological entropy is finite. And also, topological entropy cannot increase under factor maps. So if you want a subshift of finite type that factors into every effective action, you would need to have that every effective action has finite entropy, right? Because no action with infinity entropy can be the factor of a subshift. But well, if gamma is recursively presented, you can always find effectively closed actions with infinite entropy. For instance, the inverse limit of the full shift on n simples, right? So this is a very dumb reason, but it shows you that there's no hope of being self-simulable for amenable groups. Okay? Okay, so all right, amenable groups are out of the question. I also told you that a few other non-amenable groups are out of the question. What we actually showed is the following. If I graph the direct product of any pair of non-amenable finitely generated groups, then you are actually self-simulable. Okay, so why is this?
So hang on. So the free group times the free group is self-simulable?
Yeah, if you mean free group on two or more
Two
elements,
generators,
yes.
yeah.
Yeah.
And oh, I see this. Yeah. Okay.
Yeah, that's self-simulable. So every effective thing that you can define is the factor of an SFT. And the proof is easy. That's the nice thing. If you know the former proofs in Z square or Z or whatever, they always involve hard things like substitutive structures, hierarchical structures, very complicated constructions. Well, this construction is also technical, but it's considerably easier. So we won't need anything hierarchical. It's actually based on the existence of paradoxical decompositions from non-amenable groups, which looks pretty. And the technique is very flexible. And you can prove other things using this technique. So I think it's worthwhile to tell you a little bit about the technique that we use to prove the theorem. So let me just remind you what is a non-amenable group. So the definition is that one. A non-amenable group is a group which is not amenable. Perfect. Now we can work with that one. But of course, you want to use something nicer. A group is non-amenable if it admits a paradoxical decomposition. So what is a paradoxical decomposition? Well, essentially, it's Banach-Tarski. It means that I can partition my group in two disjoint sets, A and B. And then if I grab these two disjoint sets, I can again partition them into finitely many sets each. So A, I partition it into A1 up to AN, B into B1 up to BK. And then if I take these sets A1 up to AN and I translate them in a particular way, I cover the whole group disjointly, and the same thing with B. So this is better with a picture. Take the free group and take these partitions. So I'm gonna partition gamma into red and green. Red means A1 union A2. Green means B1 union B2 and B3. Okay, so it's exactly what you see there. This left side is A1, this right side is A2, etc. So, okay, that's my paradoxical decomposition. And why is it paradoxical? Because if I grab A1 and A2 and I move A2 to the left, I cover the whole group. Okay, so the A's, if I translate them somehow, I cover the whole group. Now let's go back. I want to cover the whole group with V. Well, the only thing that I would need to do is grab V1 and move it down, right? If I move V down by one position, I cover everything again. So these are paradoxical decompositions, right? They allow me to cover the group, and it's actually how you prove Banach-Tarski and things like that, right? It's essentially because the unitary grouping of the sphere in 3D is non-amenable. Okay. So the nice thing is that these paradoxical decompositions can be expressed analytically. There's a functional way of expressing the existence of paradoxical decompositions, and it's the following. A group gamma is non-amenable if and only if there exists a finite set K and a 2-to-1 map from gamma to gamma such that G minus 1 phi of G is in K for every G in gamma. So essentially, it means that I can double my group, right? This K is essentially coding the set of moves of the paradoxical decomposition. If you've seen how the proof of existence of paradoxical decompositions goes, you actually prove this first before showing the existence of paradoxical decompositions. You blow up a contradiction to the Folder sets, and then you use the Hall's cis-het marriage theorem, right? Okay, so the nice thing is when I look at these maps, these 2-to-1 maps, the collection of all such maps can be coded using a subshift of finite type. And that's the main thing that I want to notice. I just want 2-to-1 functions from the group to the group such that the images are bounded. That's what the condition downstairs says. G-1 phi of G is in K means that the images cannot jump a long distance. They just remain bounded. So how am I going to code the space of all such functions? Well, I'm going to take as alphabet K to the 3 times green and blue, 2 colors. I'm going to think of this K3 as 3 directions. One is pointing to the image, the other 2 are pointing to the pre-images. And the color is going to help me partition this into which is the first arrow and which is the second arrow. So picture. These are the element. This is the alphabet of my subshift. At every element, I'm going to assign an outgoing arrow. Think of K3 with a color, either green or blue. And I'm going to have 2 incoming arrows, K1 and K2. One is going to be green, the other one's going to be blue. And I'm going to impose some conditions such that A and B are different. So we have 2 different pre-images. And these things are actually correspond to the coding the 2-to-1 map. Right? All right, that's my alphabet. My local rules are obvious. I'm just gonna force that whenever I have a point C and it's pointing towards A, and then I follow back the blue arrow, I get to the original point. Same thing with the green arrows. Everybody must have an incoming green and an incoming blue, etc., etc., etc. So essentially, what I'm gonna create is this kind of binary tree structure. Right? With this 2-to-1 map, I'm going to induce a binary tree structure. Now, that's slightly misleading. I don't really have a binary tree structure. Why? Because the outgoing arrows might point to themselves, or they might form a cycle. But trust me that that's not going to be relevant. Okay? All right, so essentially, the only thing important is that for every element, I'm going to have 2 kinds of arrows pointing to it of 2 different colors. So for the moment, bear with me and believe that I have an infinite binary tree. There is a canonical way to assign a one-sided infinite path to every node such that they don't intersect. Well, imagine I have this node at the top. I could assign to this green node the blue path pointing to it. Right? To this one here, I assign the blue path pointing to it. To this blue node, I assign the green path. And the point is that if I do that, the paths do not intersect, except possibly on the first vertex. But if I remove that one, the paths are all disjoint. So what I obtain is that if I assign the incoming arrow of the opposite color that I'm pointing out, then the paths do not intersect. So essentially what I can prove in my subshift is the following. In every non-amenable group, I can find a subshift of finite type, which we call the paradoxical shift, and a continuous function from P times N times gamma to gamma, such that this map is 1-to-1. So in words, in every configuration of the paradoxical shift, if I stop at one element of the group, through local rules, I can deduce a one-sided infinite path, and all these one-sided infinite paths are disjoint. So this is very nice. To every element of the group, I can find an infinite sequence of elements of the group, and they are all close. They are at bounded distance. I do only bounded jumps, which are described by my configuration, and these paths are all pairwise disjoint. So I somehow gained space, right? If I want to do something, some computation on an element of the group, now I have a whole line to do it. Okay. So here's our trick.
So is this done in such a way that, so if I look at G and gamma, and I look at the path that's associated to it, if I look at another point that's on that path, is the path that's associated to that point just a subpath, or is it completely disjoint?
It's disjoint.
Oh,
it's
okay.
disjoint. So you should think of that path as, say my element G had an outgoing blue arrow. So my path are all the green arrows that are pointing to this point. So at any moment in this path, all the nodes are green. So the path associated to that element is disjoint, because then I follow the blue arrows.
Okay.
So they are all disjoint, pairwise disjoint.
Okay.
All right, so
yeah, interesting.
that's the main trick. So now for computation, one-sided paths do not suffice, but we know a lot of things that we can do with grids. So we are just greedy. So we take the product of two non-amenable groups and we do the following trick. I take the paradoxical subshift on each component. I extend it trivially to the other component, and I take their product. So now I get a subshift of finite type on this direct product of two non-amenable groups, such that to every element of this product, it associates a grid. So every element on gamma, now the product of two finitely generated non-amenable groups, has its own grid where it can do whatever it wants. Okay, so through local rules, through a subshift of finite type, I associated a grid to every single element, and that's the interesting part. Okay, and now what do I do with this grid? Computation. So we are going to use these grids to encode the computation of a Turing machine using Wong tilings. So this is a very old trick. This is not ours. If I have a Turing machine with alphabet sigma, states q, starting states q0, and a transition function delta, I can encode its the sequence of configurations that it passes by using these tiles. So I just have a starting tile that says I start with state q0 at A. I have a tile that marks every element of the alphabet. That's just the base. And then using the transition function, I just construct these tiles that force me to move deterministically. So this is kind of what I see if I try to tile n squared by putting the q0 A tile on the bottom left, right? So I put the starting state on the bottom left with something, and then I run. And this thing is gonna fill up n squared deterministically, right? It's just gonna start computing. And if I look at the sequence of symbols, it corresponds to what the Turing machine does after n iterations on row n. Okay, this is a very, very old technique. So what's the trick? Okay, I'm gonna take the alphabet of the set representation as the alphabet of my Turing machine and use it as tape alphabet. I'm gonna encode the Turing machine which enumerates all the cylinders which are in the complement of the set representation. And I'm gonna take out of my Wong tiling all the tiles that contain the accepting state. So in other words, the only remaining configurations will be the ones that such that the Turing machine never stops, right? The Turing machine is searching for words that are forbidden. So what I'm gonna do is if it looks at a word, if it finds a word which is forbidden, it tests the prefix for a number of steps. If at some point it figures out, oh, this is forbidden, this configuration is not there, it goes to the halting state. But I removed that one tile. So that will not tile n squared. In other words, if this happens to tile n squared, the configuration in the base is in the space, right? So it will only end up with configurations that are in the set representation, right? So here's an illustration of that. I put here my configuration x0, blah, 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 blah. I run my Turing machine, and if I happen to tile n squared, then I'm good, right? If this survives, then x is in the set representation of my action. Okay, so now I'm almost done. We have a subshift that assigns to every g in gamma an n squared grid. Now we put through local rules these Wong tilings on top of every n squared grid. So now I'm sure that for every g, I have encoded in this grid an element of the set representation. So the element of the set representation, remember, it has a point, and it also has all of its images under some generating set. I'm going to take the generating set, of course, of gamma. So the only thing that I need to do now is to communicate adjacent grids, right? So for every g in G, I have encoded xg s in S for a generating set. So the only thing that I have to do now is to weave this n squared grids together, imposing that when I move from an element G to G times S for some generator, then the configurations that I'm encoding, well, they match. But how do they match? Well, I encoded the configuration and all of its images. And these things will be at a bounded distance, so I can check symbol by symbol that these things do match. So after I weave them together through local rules, all these grids will be coordinated and correspond to an actual orbit of the system. So the only thing that remains is to factor at the configuration in the identity, and that gives me the factor map from this subfield of finite type to the effective action. Okay, so of course I'm hiding a lot of small technical details, but essentially this is the proof. So great, it means that for any product of two finitely generated non-amenable groups, this thing is self-simulable. Every effective action is the factor of an SFT.
But hang on, hang on.
Okay, I will hang on.
What happens to your entropy argument? I mean, if you take Sulfic,
don't shift non-amenable groups.
No. But don't. Just a minute. Don't shifts of finite type have finite Sulfic entropy with respect to any Sulfic approximation?
I think that the paradoxical shift is not going to have any invariant measures on it. And so the Sulfic entropy will be minus infinity, because that's just that's what happens whenever you don't have any invariant measures. Basically, the Sulfic entropy theory machinery doesn't work here. We don't have any good models on any finite approximations
of the paradoxical SFT.
Yeah.
Oh, so that's it's not infinite. It's minus infinite entropy.
Minus infinity. Yeah, good question.
Jesus. Okay.
Yeah, so in fact, if you want to use this for something like classification of entropies or something, it doesn't work at all. Okay, so all right, I have this result that the direct product of any pair of non-amenable finitely generated groups is self-simulable, and I'm very happy because I know these groups do exist. But of course, this class is kind of artificial, right? I don't think when I want to prove that groups are self-simulable, they are usually not direct products. But so the next step is to prove some stability properties. We proved it's not so hard to show that self-simulable groups are stable under commensurability. So two groups are commensurable if they have finite index subgroups which are isomorphic. So that preserves self-simulability. And also, if you look at finitely presented groups, this class of self-simulable groups is stable under quasi-isometry. So the argument here is very similar. You can code the space of quasi-isometries of a group into another group with an SFT. So you do a very huge coding that encodes quasi-isometries, and you can transfer self-simulability from one group to another, as long as they are finitely presented. And here, finitely presented seems to be important, although we do not have a counterexample, but I think it's important. We also proved that if you have a group which has a normal self-simulable subgroup, then you are automatically self-simulable. And we proved something slightly stronger, which means that if I have a group generated by a finite set, which has a self-simulable subgroup, not necessarily normal, with the property that delta intersected with the conjugated version of delta is non-amenable for every S in this generating set, then gamma is self-simulable. Okay, this gets technical. This is just a technical condition to transfer information through the cosets. The proof is not so complicated, but it's very nice because it allows us to prove that many interesting groups are self-simulable. So if I use the last property of this class, we get a very nice lemma that allows me to prove that many groups are self-simulable. So this is the lemma. I give you a finitely generated group which has a faithful action on the Cantor space with the property that any non-empty open set satisfies that the subgroup which fixes the complement is non-amenable. Suppose I have a group like that, a group action like that. Then this group is automatically self-simulable. How does the proof go? Well, essentially it uses this last property. And what we do is, well, we take just two disjoint open sets, and as the action is faithful, these subgroups must commute. So I have two commuting non-amenable groups. I play around with them a little bit, and I can get to the last condition. Okay, so this is a handy way of proving that a group is self-simulable. And a corollary of that is that Thompson's V is self-simulable. So here is the proof sketch. I consider the natural action of V on 0, 1 to the n. If I fix any non-trivial word, the subgroup which fixes the complement is isomorphic to B. B is non-amenable. So I satisfy the lemma, boom, this group is self-simulable. Okay, so essentially I'm hiding that this group contains many copies of these that kinda commute between themselves. Okay, all right, so that's nice. And so here's again this very old and hard question: is Thompson's F amenable? We don't know, but we proved that Thompson's F is self-simulable if and only if F is non-amenable. So amenability of Thompson's F is equal to Thompson's F not being self-simulable, meaning there is an effective action which is not the factor of an SFT. If you find me any such action, then it is amenable. Okay, so here's the proof. This group is finitely presented and so recursively presented, and I told you that amenable recursively presented groups are never self-simulable. So if F were amenable, then this thing is not self-simulable. On the other direction, I consider the natural action and I replicate exactly the same proof as above. If I fix a word, the subgroup of F that fixes the complement of a word is isomorphic to F. I could think of it, it's easier to think of it as homomorphisms of the interval. If I just look at Thompson fixing the rest outside of a finite interval, it's the identity. And in this small square, well, I get exactly Thompson's F, right? So, well, it satisfies the condition of the lemma. And so if it is non-amenable, well, if it is non-amenable, it satisfies the condition of the lemma, and thus it must be self-simulable. So we get this very nice way to prove that F is amenable. Find an effectively closed action which is not the factor of an F subshift of finite type. I have no idea how to prove that something is not the factor of an F subshift of finite type. So if somebody figures a way to do this, it might be very worthwhile, right? And just as a side remark, I can show that if F is non-amenable, then T is also self-simulable because of the same argument. If you restrict T, you get copies of F. Okay, just to tell you some extra things that we got. The following groups are self-simulable through different techniques using the properties that I told you above. Finitely generated non-amenable branch groups. They are all non-amenable. The finitely presented simple groups of Burger and Moses. This is through a quasi-isometry argument. They are all quasi-isometric to the product of F2 times F2. Thompson's V and higher dimensional Thompson's V groups bring Thompson's groups and V, if you know what they are. And the next one you probably know, general linear groups GLNZ and special linear groups SLNZ for n bigger or equal than 5. So on dimension 5 or more, these are self-simulable. For dimension 2, they are not self-simulable because they are virtually F2. And for 3 and 4, we have no idea. Same thing, the automorphism group of the free group, an automorphism group of the free group on at least 5 generators, self-simulable. Break groups on at least 7 strands, self-simulable. And if you know what right-angled darting groups are, there's a technical condition that ensures that they are self-simulable. Okay, so just playing with the above properties, we got a lot of groups, and you probably heard about a few of these, right? So these groups do happen naturally. They're not just direct products of things. And there are other applications that I should mention. there is this very nice question of which groups admit free subshifts of finite type. So subshifts of finite type which act where the shift action is free. And this gives me a way of doing it, because if I admit a free effectively closed action and the group is self-simulable, then the shift action is free on the subshift of finite type. The proof is very easy, right? It's just pushing periodicity through the factor map. If I have some period on the subshift of finite type and I apply the factor map, I get one on the factor, right? So if the factor is free, then the subshift of finite type must also be free, right? Funny thing, if I have a finitely generated group with decidable word problem, there's always an effectively closed gamma subshift, which is free. That is something we proved a few years ago using probability techniques. And the corollary is that every self-simulable group with decidable word problem admits a gamma SFT where the action is free. Okay, so these are also called strongly aperiodic. You can always have strongly aperiodic gamma subshifts of finite type on self-simulable groups with decidable word problem. So here's a few examples. Direct products of free groups. They have this property, Thompson's V, braid groups, GLNZ, SLNZ, etc. Okay, and last remark, this computability property that I said that gamma has decidable word problem is important, because you can actually prove that this gamma is finitely generated and recursively presented but has undecidable word problem. Then there are actually no free effectively closed actions. So the decidability of the word problem is essential to this corollary. Okay, that's an old theorem of Emmanuel Jandel, the node. Okay, this is all I wanted to say. Thank you very much for your attention.
So great, let's thank Sebastian. Great, so I'll just open it up for questions. So anybody have a question, just unmute and ask.
So how about the automorphism group of a full shift?
I have no idea. So that's not finitely generated?
No.
So the question's really for just because, I mean, you could define effective actions.
Hey, Jeff, how are you? Good, how are you? Good. Thanks for coming back.
Sorry.
Sorry,
Okay, no, fine, don't worry. So it's technically you can define effectively closed actions for
it's certainly some sort of, I mean, these are all